The only time you see it is when one of the two bodies is the size of a planet. If one of the bodies is literally as big as a planet, well then you'll see gravity at work. And that's what happens, of course, to the apple. Think of the apple as the small m, the Earth is the big M, the Earth is pulling the apple, and it pulls it with a force proportional to the separation between them. You all get it? So that's what's going on. Now, that was very interesting, but of course what Newton did was he went a step further. He really was a revolutionary thinker. What he said is, oh, well, that's what's going on in the sun as well. What's happening is the reason the Earth goes around the sun is that the sun is pulling the Earth, and Jupiter and all those other planets. That's why they're going around the sun. So gravity is caused by the sun's mass. In the same way that terrestrial gravity is due to the Earth's mass, the gravity around the sun is caused by the mass of the sun. Now, you all probably find this fairly boring because we're so used to it now. But at the time, that was an incredibly, incredibly surprising idea. And if you think about it, it still is. Because, I mean, you've all heard of maybe positive charge attracting negative charge, or maybe magnetism going this way and that way. But what is it about mass that's inside the computer that somehow can attract the microphone? That's a very mysterious thing. To this day, we don't really know. The big mystery is, what is it about mass? Okay, the Earth is very big and heavy and all that. Yes, but that doesn't explain what is it in its nature that's pulling things around it. How does gravity actually work? And that's the sort of thing that mathematicians worry about all the time. So let's move on. Having got that idea, how does that apply to the universe? Well, we've established that this is probably the main force in the universe is gravity. It's a long-range force. It's always attractive, pulling things together. It's cumulative, as in if you have something that's bigger and bigger like a planet, gravity goes up. It holds the solar system together, and it also holds local galaxies together. Like our galaxy, the Milky Way, is part of a cluster of galaxies. And what's holding that cluster of galaxies together is gravity. Then you might wonder, well, are there any other forces? The answer is yes. Let's just briefly look at them. You've all heard of electricity. Well, that's basically the electromagnetic force, which is electricity and magnetism together. That holds atoms together. But the thing about that force is it doesn't really affect things at long range. And the reason is because it's a very, very strong force. So something that is positive very quickly gets together with something that's negative. There's no singles in electricity. You very, very quickly marry something of opposite charge because it's a very, very strong force. So if you have a proton somewhere in this building and there's an electron anywhere in Ireland, it'll find that electron very, very quickly. So at long ranges, the electromagnetic force tends to be neutral. So it doesn't really affect things on the cosmological scale. Then there's two other first forces. You may have heard of the nucleus. That's what's inside the atom. The very, very part of the atom is the nucleus. The strong nuclear force is what's holding it together. Some of you who've met this in school, you've hopefully wondered by now, yeah, we know there's the atom, you've got the nucleus inside, you've got the protons inside the nucleus. Yeah, but hang on a sec. If the protons are positively charged, how are they sitting there in the nucleus? Are they not flying apart if they're all positive? And the answer to that is yes, that's true, but that's because there's an extra force called a strong nuclear force. And there's also a weak nuclear force, which is to do with radioactivity, but we don't have to bother with those because those are all short-range things, so they won't affect our discussion of cosmology. Okay, so that's pretty much what was known about cosmology right up to the 20th century, and then all hell broke loose in 1929. And what happened there was powerful telescopes had been developed. People had begun to realize that our solar system is only one solar system in a whole shebang called the Milky Way. That's our local galaxy, the Milky Way. But the big discovery was, well, there's two big discoveries. The first one was this guy, Edwin Hubble, working in the States, an American, discovered that the Milky Way is only one galaxy, and there's actually lots of galaxies out there. Again, we all find that obvious now, but it's not obvious at all if you look at the sky. You might think, well, it's just loads of stars. But it turns out there's big clusters of stars and galaxies, and there's lots of different galaxies. So that was his first big discovery. But the really shocking thing, which most people in maths would say is the biggest discovery in science in the 20th century, probably the biggest of all the discoveries we've made, the biggest is that the galaxies are actually moving apart. They're not stationary. Everybody assumed the universe is just stuck there. But it turns out, just like presumably the Earth had a beginning and will one day have an end, it looks like the galaxies are moving, constantly moving all the time. And that raises a whole load of questions. Oh yeah, I should quickly say, how do we know that? How does anybody measure this kind of stuff? Well, the answer is, you know the way when you're standing there and an ambulance goes past, an ambulance doesn't actually technically go, nee-no, nee-no, nee-no. That's not what an ambulance does. What an ambulance does, if you listen, you have a good ear, you'll hear, an ambulance goes, nee-no, 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 nee-no. The actual pitch of the note changes, and I'm sure you've noticed that. Or to turn it around, it's very frightening if you're sitting at a red traffic light and an ambulance comes up behind you, Because not only is it getting louder because it's coming towards you, it's coming closer, but the pitch actually goes up. So it goes nino, 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 and it goes higher and higher, and it's actually quite unnerving. Well, the same thing happens with light. If something emits light, if it's moving away from you, the frequency of that light actually changes. And it turns out in physics, as the frequency changes, so does the color. So when stars move away from us, the color changes. And that's how they discovered. This guy, going back here, this guy here was looking at the light emitted by stars in these faraway galaxies. And he found, my God, it's redshifted. And redshifted in physics means absolutely unequivocally, those things are moving away from us. And they're moving away from us very, very quickly. So that was a massive, massive discovery. This is the only graph I'll show you. And it looks really complicated, but it's not. It just turns out if you look at the speed, if you plot the speed of a galaxy versus distance, what it comes down to is a galaxy that's twice as far away as another is moving twice as fast. The furthest galaxy from us is moving the quickest from us. The nearest galaxy to us is moving the slowest. So the further it is, the faster it's moving. And that's a very uncomfortable idea, because what that basically means in English is that the universe as we know it is expanding. It's not stuck in one place, it's getting bigger and bigger and bigger and bigger. And it's continuing to do that, and there's no reason to suppose that that's going to change. So that was the first big discovery. That's 1929. I would say the biggest discovery of 20th century science, that the universe is actually expanding all the time. It's not stuck. Everyone assumed it was there forever, had no beginning or end. But not at all. It's changing all the time. Let's look at the consequences of that. The first person to really think this through was a Belgian priest called George Lemaître. And George was a pure mathematician, wouldn't know a laboratory if you hit him over the head with it, nothing about physics. But he looked at the Hubble graph and he said, well, wait a minute, let's look at that again. What happens if instead of looking that way, if you rewind the tape? What happens if you go backwards? In other words, look at the origin. He's going backwards on that, and he said, well, if we rewind that, doesn't that mean that at some stage all those galaxies, just like the movie you saw, all those galaxies originally were together? Because if they're moving apart now, they must have been closer yesterday, and the day before they must have been closer, and the day before that. So if there's enough time, what happened was originally they converge. Converging means things coming together. And that was the first beginning of the idea of that time had a beginning. And time is called the Big Bang. So the beginning of that time is called the Big Bang. Hopefully some of you will have heard of a very famous book now by Stephen Hawking called A Brief History of Time. That's what he meant by that title, A Brief History of Time. Because time itself will begin then at the beginning of the universe, because time is part of the universe. And that's what we call the Big Bang. Now, if it did happen that way, what would happen then is as the universe expanded, things would cool down. Why? Because when things are together, they're extremely hot. As they move outwards, the temperature, the density goes down, things begin to cool down. So we think of the universe as starting extremely hot, and then as it moves out, over time it begins to cool down. Now, immediately you might think, yeah, well, that's kind of like philosophy, it's a nice idea, and it's very exciting, but how much practical use is it? Well, an immediate practical example that this young priest, and he was quite young, immediate practical example he thought of himself was, actually, we can work out how old the universe is. There's a little bit of math there on this side, you needn't worry about too much if you don't like it, but speed, or velocity. Speed is basically distance over time, but we also know the speed from the graph. So from the graph, we can actually work out what the time is. And when you work out what the time elapsed from the origin is, from the slope of the graph, you get an answer that time is about 14 billion years. And a lot of people got reasonably excited when they saw that, because up to this point that was just, it's a man Lemaître with this little idea. But he used to sort of go up to Einstein in conferences and say, I've got this idea, and Einstein would say, go away. But at this stage, people started getting interested because 14 billion years is about right. And how do we know that? Because the oldest rocks in meteorites, for example, are always a couple of billion years old. So this was in the right ballpark immediately, and then people started sort of thinking, well, maybe that's an idea. So let's wrap up the beginning. That's our first big idea. That basically, about 14 billion years ago, a billion is 1,000 million, so it's not that long ago, about 14 billion years ago, the universe started basically at a point smaller than this apple. Some sort of cataclysmic explosion occurred of everything, matter, space, and time, and the universe has basically been expanding and cooling ever since. So that's what we mean by the Big Bang. Okay? And that's basically all that was known about it, right up to about, I think, 1940. So that was the beginning of the 20th century. From 1900 to 1940, they basically established this idea.